Okay, so in the end of the last video I introduced the standard model, which is a description of all of the fundamental particles that we know about in the universe so far. And in that lecture I talked specifically about these quarks, which are the building blocks of particles like protons and neutrons, which collectively are known as the baryons, and also bosonic particles known as mesons. Okay. And we also talked about the electron and its similar particles, muon and tauon, and their neutrinos, which together form the lepton group of particles. Okay, so the ones we didn't talk about last time, which we are going to talk about in this video, are these five here. So there are these four gauge bosons, the photon, the gluon, the Z boson, and the W boson. And there's also the Higgs boson here. Okay. So first of all, we'll talk about the gauge bosons. Whoa, why? Okay. Oh, that's on a different presentation. Sorry. Here. Right. Okay. So here again are the four gauge bosons. Okay. You can see they all have spin 1, and bosons must have integer spin. And the first three of them are chargeless. So the photon, the gluon, and the Z boson are chargeless, whereas the W boson has a charge, so it does interact with the electromagnetic force. And the photon and the gluon are massless, whereas these Z and W bosons have mass. And this mass here is very important to describe the importance of the Higgs boson, which we'll do in the next few slides. Okay. So I want to start by talking about the electromagnetic force, because this is the one where we kind of know the picture. So the idea is for a certain property, in this case the charge of a particle, gives rise to a particular field or force, in this case which is the electromagnetic force, and then the quantization of this force, as we've seen, is the photon. Okay, so the photon is the quantum particle corresponding to the electromagnetic field, which generates the electromagnetic force. And this is what we mean by a gauge boson. A gauge boson is the quantization of one of these force fields. Okay. So if I write the kind of connection up here, there's my pen. Need to plug it in again. Okay. So you start with a particular force, in this case the electromagnetic force, okay, and that is generated by a particular property of particles, which is known as the charge, and the quantization of the field in this case gives rise to a gauge boson, which in this case is called the photon. Okay, so this connection is true of the other forces as well. Right, so what are the other forces? Well, it was known that there must be other forces which are holding the nucleus together, because the nucleus is only made up of protons and neutrons, so neutrons do not interact with the electromagnetic force, because they're neutral, and protons are all positively charged, so actually they would try to push each other apart. So there must be a stronger nuclear force which is holding all the protons and neutrons together. And it turns out there are two kinds of forces which act on these particles, which are known as the weak force and the strong force. Originally they were called the weak nuclear force and the strong nuclear force, but now the word nuclear is usually dropped because, in fact, although the strong force is reasonable to call the strong nuclear force because it only acts upon particles made up of quarks, which form the nuclei, protons and neutrons, this weak force actually all leptons and quarks interact via the weak force. Okay, so the electron also experiences the weak force, so it's not really right to describe it as a nuclear force. Okay. So there's also gravitational forces. Gravity is a very, very special case, which, okay, I will mention briefly, but basically we still have no idea how to make the quantum theory. Okay, but for these others, the weak and the strong force, the picture is kind of, the picture is similar to the electromagnetic field in the photon. So there's a given property of a particle which generates the field. In the case of the weak force, it's known as the weak isospin, which you may well not have heard of before, but don't worry if you haven't. So this is a property that all particles have, like the charge. And if a particle has a non-zero weak isospin, then that means it interacts via the weak force. Okay, and the quantization of the weak force gives rise to, in this case, 3 different particles, the Z boson and the W plus and the W minus. So here, these two are particle and antiparticle, right? For each particle with a positive charge, there must be an antiparticle with a negative charge. And these are just written as W plus and W minus, like this. Okay, and the same is true for the strong force. So if I write the same thing for the strong force, the strong force is generated by something known as color charge, which is going to be on the next slide. So this generates the strong force, and then the quantization of the strong force are these particles known as gluons. Okay, so that explains what all of these 4 particles are in detail. The photon generates the electromagnetic interaction between particles, the gluon is the strong interaction, and these Z and W are the weak interaction. Okay, so first of all, we'll talk about the strong force. What is color charge? Okay, so the color, the name of the color is just to give you a kind of natural way of thinking about it. There is no real color in the sense that we're used to in this strong nuclear force. But the point is that if you look at the electric charge, then there's only 2 possibilities, right? It can be positive or it can be negative, right? So it forms like a one-dimensional line of charge. There's 0 charge, you can have positive charges or negative charges, right? But for the color charge, it turns out that there are kind of 3 directions you can go on, which are kind of ranged in some sense in a triangle like this, 120 degrees. And to work out the total color charge, you add together these 3 different vectors. Okay, so these 3 different vectors have, you can't just call them plus or minus because there's 3 of them. So they have 3 different names, and it's chosen to name them after the primary colors. So one is called red, one is called green, and one is called blue, like this. Okay, so the antiparticles, just like an antiparticle has the opposite charge, the antiparticle will also have the opposite color charge. So they are given by the vectors in the opposite directions here, which are known as the anti-red, anti-green, and anti-blue. And just as when you make an atom is electrically neutral, so that means the positive charge in the center of the atom has to be balanced by the negative charge around the nucleus. The same is true of the mesons and baryons. So although a particular quark has one single color, so for example an up quark can be blue or red or green, as shown in this picture here. This is an image of a proton here, so 2 up quarks and a down quark. So it has, in this example, a blue charged up quark, a red charged up quark, and a green charged down quark. And if you add up the total charge, then you get 0, because adding up the color charge means you're adding up the vectors in this diagram here. And you can see if you add up a blue vector, which looks like this, to a red vector, which looks like that, and then to a green vector, which takes you back there, then you get back to 0, right? So this total proton here has 0 color charge, okay, even though the parts that make it up, these quarks, have charge. Okay, so mesons, because they're made of just 1 quark and 1 antiquark, and the antiquark has this anti-color charge, they must always be of 1 color and its anti-color. So in this case, in this example, this is a pi plus meson, which is made up of 1 up quark and 1 down quark. Okay. In this case, the up quark is blue, and the anti-down quark is anti-blue. So if you add those 2 up, you go here and then back to 0. So again, it's color charge neutral. Okay, so that's all about the strong force and the color charge. So there's an interesting question: can you get particles of 0 charge by adding up sort of 2, 3, or 4 of these or 5 of these? So in principle, it can be done as long as you combine quarks and antiquarks together. But these 4 quark, 5 quark particles have never been observed in nature. So we think in nature they only come in either quark-antiquark pairs like this to make a meson, or 3 quarks together to make a baryon. Okay, so next the weak force. And like I said, the weak force, although it was discovered initially in the context of the nucleus because it's responsible for beta decay, it actually applies to leptons and other particles as well. In particular, all fermions in the standard model we think do have a weak force interaction, so that includes the electrons and the neutrinos and so on. And this is actually how we can detect the neutrino, because the neutrino has no charge, so it doesn't interact with electromagnetic forces. It also has no color charge, so it doesn't interact with strong nuclear forces. So the only interactions it has are gravitational or weak force interactions. The gravitational force is much, much weaker than any other force. And therefore, the only way we can detect neutrinos is through detecting their weak force interactions with other particles. Okay, so like I said, beta decay is an example of a weak force interaction, and beta decay is written by the equation here. And what's going on in terms of quarks? Well, the neutron is an up quark and 2 down quarks, and the proton is 2 up quarks and a down quark. And then you have also an electron and an anti-electron neutrino generated in the beta decay. And you see what's happened here is that one of the quarks has changed from a down quark here into an up quark here. So this is known as quark flavor change. For some reason, rather than talking about up, down, charm, strange, and so on as the quark type, it's called the quark flavor. Okay, that's just a strange terminology. I don't know why it's called that, but yeah, rather than talking of up and down quark types, we talk about up and down quark flavors. So when a down turns into an up, we call that a quark flavor change. Okay, and that's exactly what happens with this beta decay. You start with a neutron, then one of the down quarks, in this example the blue charged down quark, turns into an up quark, and obviously that doesn't conserve charge, right? Because the charge on the down quark, the electric charge I'm talking about now, was minus 1/3, and the charge on the up quark is plus 2/3. So you see, to go from down to up, you've gained +1 charge. So in order to conserve charge, you must also create a negatively charged particle, and this is where the weak force comes in. So the charge is conserved by creating this weak force, in this case a W- particle. And the W- particle itself decays, and when it decays it produces 1 electron and 1 anti-electron neutrino. Okay. So these particles, the W- and the W+ and the Z0, are the only particles which can change one kind of quark into another. Via the strong force or via the electromagnetic force, the type of quark, the flavor of quark, must stay the same throughout the interaction. Okay, but for example, you could have a strange quark turning into a down quark, okay, and it would do so by also creating a Z0 weak force boson. Okay, okay, or you could have an up quark turning into a down quark, and in this case, to conserve charge, you would create a W+ boson. Okay. Okay, so this is what the weak force looks like, and like I said, this is the only way we know that one flavor of quark can turn into another flavor of quark. Okay, so finally we get to the Higgs boson. I think this is the last slide, or there's one more. Okay. So the Higgs boson, again, was one of these particles like the neutrino that was predicted a long time before it was discovered. So it was predicted in 1964 by a whole group of people, including Peter Higgs, who it's now named after. But there were lots of other scientists who came up with similar ideas about the same time. And it wasn't actually detected until just a few years ago, about 2013, depending upon when you accept the level of evidence is sufficient to say it's been discovered. But around 2013, this was actually one of the main reasons for building the Large Hadron Collider, to try and detect this particle, and they were successful in doing so. So just like in the neutrino was predicted because there was a problem with the experiments and the theory. In particular, the beta decay experiments showed that it looked like energy was not being conserved. Energy not being conserved is a serious theoretical problem. So in order to solve this problem, Pauli predicted the existence of the neutrino. The Higgs is a kind of similar story. If we go back and look at these fundamental gauge bosons here, I told you that the weak force gauge bosons have mass, okay? But the theory here says that gauge bosons cannot have mass, okay? Exactly explaining why is way beyond what I can do in this course. But the theory of particle physics says that gauge bosons must have zero mass. Okay, and this is the problem, because the experiment is saying no, these particles definitely don't have zero mass. They have actually very large mass. This is like 91 times the mass of a proton or more. Okay, so they're very big mass. So where does this mass come from? So the idea to explain it in detail is quite complicated, and one of the student presentations is on the Higgs boson. So hopefully the person presenting on that will explain in a bit more detail. But the basic idea is that the mass comes from interactions. So one of the things we learnt in special relativity is if you increase the energy of a particle or a system of particles, then you also increase the mass, right? So the interaction energy produces mass. And you can see that, in fact, with the fundamental particles. If I go back to the other presentation for a moment, this one, if we were to look at a proton is made up of two up quarks and a down quark, and the mass of the proton is about 1 gigaelectron volt, just under like 980-ish mega electron volts. But if you look at the mass of the up quark, so two up quarks and a down quark, then the total mass of these particles is 2.4 plus 2.4 plus 4.8. So altogether that's about 10 MeV. So you see that the proton is actually 100 times more massive than the sum of the masses of its particles, and the reason is the rest of the mass of the proton comes from interaction energy, from this strong force interaction going on between the quarks within the proton. So the rest of the proton mass comes from interaction energy. Okay, so the idea of Higgs and these other scientists is maybe we can describe this mass for the Z and W bosons by the same mechanism. Maybe the particle by itself is massless, but by interacting with another particle, because of that interaction energy, it acquires a mass. Okay, so obviously you have to do much more than that to make this theory, which these people did. So you have to say, okay, what is this particle that they are interacting with? How does it behave? They predicted, for example, it has zero spin, zero charge. There were some estimations of the mass in about the right range. This is the mass energy at which it was discovered. But before that, they made predictions of about the right mass to explain this particle. And it's now known that the Higgs does not only create the mass of those Z and W bosons, but in fact it also creates the mass of all of the other particles in the Standard Model. So in the modern understanding, all of these particles are massless in a kind of isolated sense. If it was possible to just have one particle isolated from the rest of the universe, then they would all be massless, but they acquire mass through their interaction with the Higgs field or the Higgs boson. Okay. And obviously then when you start to build up particles out of them like the proton, then they acquire more mass because of the interaction energy of the other forces involved, like the strong force and the weak force and the electromagnetic force as well. Okay. Right, so just before I go on to the last slide, which is looking at conservation laws, I think I should really make a quick mention about the other force. So the other force that I haven't talked about at all is gravity. And this is, like I said, because gravity is much, much harder to quantize. If we were to quantize it, then if I try to draw a similar picture down here for gravity, then you would have to have a particle which is known as a graviton. And we know that this particle should be massless and should be chargeless, and it should have a spin 2. And this spin 2 causes no end of problems. Okay, it's basically impossible to make a conventional quantum field theory with a spin 2 particle. And we know it should be spin 2 because general relativity says it should be spin 2. So no end of theories to try and solve this problem of the quantum theory of gravity have been made. There's something known as quantum loop gravity. There's the most famous of all is string theory, which was basically an attempt to explain how gravity can be made into a quantum theory. But all of these theories have problems, either mathematical problems or problems in terms of physical evidence. Yeah, so basically in terms of gravity, we just don't know yet. Okay, right. So this is the very last slide, and this is related to how you can solve some of the worksheet questions. When scientists analyze these particle collisions and particle interactions happening within particle accelerators, one thing that helps them understand it a lot are these conservation laws. So in all of these interactions, some things are always conserved. Okay. So first of all, energy and momentum are always conserved. So by looking at the energy and momentum of the protons which started the interaction, you can learn about the energy and momentum of the particles created, which for example allows you to calculate the mass of those particles using this relationship, right, that we saw in special relativity. E squared is p squared c squared plus m squared c to the fourth. So if you measure the energy and momentum, then you can also calculate the mass of the particles. Oops, I want to go back. Okay, should discard. That's a shame. Right, okay, let me load that up again. Okay, going back here. Right, so I talked about energy and momentum here. Total electric charge is also conserved. So that was, for example, when I talked about what happened in the beta decay. Because you create a proton, you must also create a negatively charged particle, in this case an electron. Next you have this conservation of lepton numbers, which means you group the electrons into 3 groups according to whether they are electron flavor or muon flavor or tau flavor. Okay, and then you count up the number of particles, so either electrons or electron neutrinos, and subtract the number of antiparticles. This hash sign here means number. So minus the number of anti-electrons minus the number of antineutrinos, and that must be a constant, right? So as an example here, if you look at the beta decay equation up here, then obviously on the left-hand side of that equation, we have no leptons at all, right? There are no electrons or neutrinos on this side of the equation. The proton also does not contain any leptons. The electron has a lepton number of 1 for the electron case, number 3 here. Okay, and therefore, because the left-hand side the total is 0, on the right-hand side the total must also be 0. So here we need to add on an anti electron particle. But in order to conserve charge, we can't add on a positron, so we know we must add on an anti-electron neutrino here. Okay. So just starting from this, these three particles to begin with, we know that the last particle must be an anti-electron neutrino by this conservation law number 3 here. So the same thing applies for muons and for tauons. One example of where you see it for muons was actually the muon decay, which we talked about when we did the muon time dilation presentation. There, how does a muon decay? Well, a muon turns into an electron, okay? And here we can look at both conservation laws number 3 and number 4. So if I look at number 3 first, the left-hand side doesn't have any electron flavor particles. On the right-hand side, I have one electron flavor particle here, so I must cancel it with a -1. And here the correct thing to do is to take an anti-electron neutrino, again because of charge conservation. And then if I look at conservation law, if I look at conservation law number 4 here, then on the left hand side I have one muon flavor particle, and on the right hand side at the moment I have no muon flavor particles. So to conserve the muon numbers, I must add a muon neutrino as well, like this. Okay, so then this turns into a balanced equation satisfying these conservation laws. Okay, so that's 3, 4, and 5. Next, number 6 is about numbers of quarks. So if you add up all the quarks in the interaction and then take away all of the antiquarks in the interaction, then again that must be a constant. So if we look at this interaction here, I started with 3 quarks in the neutron, and then I had 3 quarks in the proton. Okay, so that's okay, and there's no antiquarks here. Okay, so another example that we can look at for the quark number conservation is actually also from the muon time dilation slide, which is over here. So here you can see there are 2 equations. So this second one here is the decay of the, in this case, the anti-muon, but that's just the same as I described for the muon, with antiparticles, of course. But first, the muon is created by a pion which decays. So here we have a pion decaying into a positively charged muon, so an anti-muon, and a mu neutrino. And if we look here, so that equation is pion turns into an anti-neutrino and an anti-muon and a mu neutrino. Then you can see on the right hand side of this equation we only have leptons, so we have no quarks. But on the left hand side of the equation we have a pion which is made up of quarks, and in particular this pion is made up of one up quark and one anti-down quark. So because on the right hand side of the equation the total number of quarks is 0, on the left hand side of the equation the total number must be 0 as well, but you see that it is, because the formula is quarks minus antiquarks, so that's 1 minus 1 here, which also agrees with that. Okay. Right, so the total number of quarks is conserved, and also if the interaction does not involve the weak force, then the number of quarks minus the number of antiquarks is conserved for each flavor of quark. Okay, so you could do something similar to 3, 4, and 5 here, looking only at looking only at up quarks, or looking only at down quarks, or looking only at charm or strange quarks separately. Okay, but in this case you can see that that doesn't work, because here we have one up quark on the left hand side which is destroyed on the right hand side, and here we have an anti-down quark on the left hand side which again disappears on the right hand side. So this means we know that this interaction, the decay of the pion, must be a weak force interaction. Okay, so the pion must first decay into this W plus gauge boson, which then can decay into a muon, or the antimuon and the mu neutrino. Okay, right, so these are all the conservation laws. So there's a question on the worksheet about it. So if we look at the week's worksheet, here, okay, questions 6 and 7 are about these particle interactions and looking at these conservation laws. So in the question 6, you have to add neutrinos or antineutrinos in order to satisfy those conservation laws number 3s, 4 and 5 for the lepton numbers. It should be fairly straightforward. Then in number 7, I give you 5 examples of particle interactions, all of which violate at least one of those conservation laws. So I just want to tell you what conservation law is violated. And also in this question, you'll see that some of these interactions involve these pi particles, and I tell you what quarks they are. So pi plus is up anti-down, pi minus is down anti-up, and the pi 0 is either up anti-up or down anti-down. And in an exam also I would tell you this. So I don't expect you to memorize a proton is 2 up quarks and a down quark, and a neutron is 2 down quarks and an up quark. That kind of information I would give you in an exam, just like I give it in the worksheet question here. But what I do expect you to do is to be able to answer these kind of particle interactions here. Okay, so to say what the conservation laws are, to say whether the conservation law is obeyed or not. Okay. Right, so just before I finish this presentation, I wanted to show you something which is interesting about this conservation, particularly of momentum, and this relates to the interaction between a particle and its antiparticle. Okay. So I'll take the case of the electron, but what I'm going to do could easily apply to a proton or any other particle. But I want to study the interaction where I have an electron and its antiparticle. And in this case, they can completely destroy each other and only produce energy in the form of light. Okay, so this is an okay interaction, but it turns out that the light cannot just be made up of a single photon in this case. And the reason for it is quite interesting, so I just wanted to explain it. If we look at a picture of what's going on, then on the left-hand side we have an electron and an anti-electron, a positron, and these are moving together and therefore they annihilate, and then after they annihilate I have a single, well, let's imagine I could have a single photon which is carrying the same amount of energy like this. Okay, so this cannot happen. You cannot get an interaction where an electron and a positron annihilate and only give you a single photon, and the reason is conservation of momentum. I can look at the same interaction in the center of mass frame. Okay, so what is the center of mass frame? Well, if you know it from Newtonian mechanics, it's exactly the same idea in relativistic mechanics. This observer S here measures the positron with momentum going in that direction and the electron with momentum going in this direction. But if I were to change observer to another observer who would have a momentum himself moving in this way with some velocity u, if I choose u to be just correct, then I can get it that from this S prime perspective, the momentum of the electron and the positron exactly cancel each other. Okay, so, and this defines the center of mass frame. So the center of mass frame is the observer for which the total 4-vector momentum, the spatial part of that 4-vector momentum is equal to 0. Okay, and such a frame always exists for collections of massive particles, right? It doesn't exist for photons because they're traveling at the speed of light, so you can never choose a frame in which they're stationary, but it does exist for collections of particles like this. Right, so now if I were to draw the same interaction from the S prime perspective, you see that you have a positron and an electron, and because the total momentum is 0, they must be traveling in equal speeds and in opposite directions like this, right? So here we have the total P, so the momentum of the electron plus the momentum of the positron is equal to 0, okay? But then we run into a problem, because then if they only produce one photon, like this, no matter what direction the photon is traveling in, the photon always carries momentum, because the photon always travels at the speed of light, so its momentum is always non-zero. So a photon cannot have total momentum P equal to 0. Okay, and this means that this decay is impossible. So therefore, to conclude, the electron plus positron cannot annihilate, that means destroy each other, and produce only one photon. Okay, it is perfectly possible for them to annihilate each other and produce two photons, right? Because if you again were to look at this from the S prime perspective over here, if I have two photons, then I can just choose photons of the same energy but heading in opposite directions like this, okay? And again here we could have, if this one is P1 and this one is P2, we can have P1 plus P2 is equal to 0, right? So again, total momentum is 0. So an electron and a positron can annihilate and produce two photons, but they can't annihilate and produce only one photon because of the conservation of momentum. Okay. Right, so I bring that up because it's interesting, and I also bring it up because this kind of analysis, looking at conservation of momentum, is important for some of the other questions on the worksheet, particularly questions 4 and 5, require you to consider the interaction in the center of mass frame. Okay. Right, so then that's all for this video, and this is the last content video of the course. So I hope the whole course has been interesting to you. There will still be one review video this week and one review video next week when we have the presentations as well. And then we only have the exam left. Okay, so that's all for now. Thanks for your attention.